to another seminar from the NSFAA Seminar Series. Today we have with us Matt Colbrook from Cambridge, and he's going to give us a talk on Cookman methods. He's an expert on it, so we're very grateful to have him today here. And as how we're going to organize him, we're going to put all of the questions at the end. So yeah, in the last 10 minutes, you can ask whatever you want. And then for the people online, you can write whatever you want in the chat, and then we can read them at the end.
Sounds great. Thank you. Do people prefer me to go to this screen or this screen? I quite like to point. So. All right, let's this. Right, so I'm going to talk about Koopman operators, and in particular, things like computing their spectra, using them to forecast dynamical systems, and also their practical limits. So I'm also going to look at situations where they don't work. So first I have to explain what a Koopman operator is. Hopefully you'll know in a few slides' time. If not, I've not done my job properly. But you can also find papers and talks on my website here as well. So I'll put the slides up at the end. Okay, so quickly before I get into the details, this is joint work with a whole host of great people, including a member of the audience here as well. But I also wanted to highlight Gustav Conradi, who's a student at Cambridge, who's doing some really nice work. So these last two papers that we'll get into towards the end. Okay, so I'm interested in dynamical systems. So in this talk, I'll look at discrete time dynamical systems. So I'll have a state space, this capital X, and then some state, this small x. And then the system will be xn equals xn plus 1 is f of xn. So this is sort of my map, f, that controls the dynamics. Okay, and then if you go into the 20th century, it was Koopman and von Neumann who started to think about, okay, what happens if we study this not by just looking at how the state evolves according to this map, but how functions of the state evolve. Okay, so think of this function g, this observable, as something like measuring the temperature of the system at a particular point or something like that. And then you define this composition operator, this Koopman operator, which takes this observable g, this function, and gives you another function just given by composition with f. There's a lot of interest in studying these operators, and in particular their spectra, so things like eigenvalues and eigenfunctions. You have to be a little bit careful about what space these functions lie in, so which functions are admissible. So throughout this talk, I'm going to look at an L2 space. Don't worry so much about that if that's a bit of maths mumbo-jumbo. Just think of this as observables with finite energy. Okay, and then we move into sort of the 21st century, and this is what a lot of people are interested in at the moment, is where you don't know this function f, or it's too complicated to analyze directly, and instead you're given snapshots. Okay, so these are pairs, data pairs, which are simply just samples of this unknown function f. So x in blue, y in green, y is f of x, so one time step forward. And I'm going to have a finite number of these observations of the system. I'm not going to specify whether that's from a single trajectory or multiple short trajectories for the time being. But what I'm interested in is the data-driven problem of using this data to try and infer something about this operator. Okay. So the first question is why? Why on earth would you make things more complicated by lifting to this space of functions on the dynamical system? And the following is an example of this. So if you take an approximate eigenfunction, g, okay, so kg equal to lambda g, that would be an eigenfunction of this operator. Think of it as a bit like a matrix. If instead you relax that condition and assume that this residual is small in some norm, let's say the residual is bounded by epsilon, then if you try and evaluate this observable, so thinking of measuring the temperature n time steps forward, for example, this is the same thing as applying the Koopman operator n times, okay, because the Koopman operator is just composition with the forward time dynamics. We know that this g is almost an eigenfunction, so we get a power of the eigenvalue here plus some error due to only approximately satisfying the eigenfunction equation. Okay, so this is great because we can predict this observable forward in time by just taking a power of an eigenvalue up to some error. And this allows you to extract things like coherent features. Okay, so here's an example on the Lorenz attractor. Each of these are g that satisfy this inequality with some small epsilon, and I'm plotting in color the value of the observable g over the state space. So the state space is the whole Lorenz attractor, so that's why you're seeing this sort of color map. And then as time evolves, you see these coherent features. Even though the system is very chaotic, very complex flow, you can still extract these coherent features. Okay, so getting these G's and these lambdas is useful. We're getting these sort of patterns. We can actually wrap this into a definition. So the approximate point, that's this AP, pseudo-spectrum of K, bit of a mouthful. All it is just all Z in the complex plane, think of Z as lambda, where there exists an observable G, where G is almost an eigenfunction up to some epsilon. Okay, so this is a relaxed version of searching for eigenfunctions of the Koopman operator. And this is what we're going to try and compute from these snapshot data. Okay, so intuitively what this Koopman operator is doing is you're taking a nonlinear, typically finite dimensional system, and then by looking at functions of the state, you trade it into a linear, but infinite dimensional system. Infinite dimensional because the space of functions is very, very big, infinite dimensional. Okay, and this leads to things like the Koopman mode decomposition. So suppose, for example, you can find a family of these G that are all approximate eigenfunctions. And let's say you're interested in a single observable. Okay, for instance, this could be a component of the state or something like that. And if you can approximately expand this observable in terms of these approximate eigenfunctions, so these coefficients are called Koopman modes, then this gives you a way to forecast. Okay, so for each individual eigenfunction, when you time step forward n times, you raise the eigenvalue to a power, and then you've got this error term here. Okay, and you should think of this as sort of like a nonlinear separation of variables through a linear operator. So this is a bit like doing a custom-made Fourier series or Fourier transform for the nonlinear dynamical system. Okay, so you can evolve H almost like a linear expansion here. Okay, so this is your sort of spatial operator, this is your temporal behavior, and this is your coefficient. Okay, so that's Koopman operators. Right, so we want to compute these approximate eigenfunctions, but there's a catch. Because we've gone to infinite dimensions, things get a little bit tricky. So if I give you a finite matrix and I ask for its eigenvalues, what do? You open MATLAB or Python or whatever, and you type eig, and then it gives you a set of eigenvalues, right? In infinite dimensions, how do you do that, right? If I give you this infinite matrix, how would you compute its eigenvalues or its spectrum? You'd probably truncate that infinite matrix to a finite matrix. Okay, so here I've got an example operator, which is called the bilateral shift. So you should think of this as acting on Fourier coefficients. So the space of functions that I'm looking at is actually little L2 of Z. Okay, so this shifts the coefficients back one. This is a unitary operator. It's very nice. Its spectrum is the unit circle. Its spectrum is stable to perturbations. It's got continuous spectra. There are no eigenvalues. Okay, and it corresponds to unitary evolution. If you truncate, you get a Jordan matrix. Okay, and if you've ever done any sort of numerical linear algebra, you know that this is something to avoid at all costs, right? The spectrum is zero. It's unstable. In fact, exponentially so in the truncation size, and it's got nilpotent evolution. Okay, so it crashes the dynamical system after a finite number of steps. So you've broken all of the nice properties of this infinite matrix by truncating. Okay, so when you go from something infinite dimensional to something finite dimensional, you have to be very careful. And the problem is that lots of Koopman operators are built up out of operators that look a little bit like this. So you see this effect. Okay. So how do people actually approximate the eigenvalues or eigenfunctions of the Koopman operator in practice? They'll probably do some version of dynamic mode decomposition, which I'm sure some of you in the room are familiar with. If not, let me explain it and also give a perhaps slightly different interpretation to the one you've seen before. So what you do is you pick a sequence of observables, okay, a finite number of these. These are sort of your basis functions or your dictionary, and you build a Galerkin approximation. So think of that as like a finite element approximation. So you need access to two types of inner products. Okay, so inside your L2 space, inner products between the basis functions themselves and when you've got the Koopman operator acting on the left-hand side here. And remember, all we've got access to are these data points. So I'm going to treat these blue points in X as quadrature points for this integral, okay, with some weights. And there's a whole literature on how you actually choose these weights, but let's not get into that. But what it boils down to is an approximation of this inner product or this correlation through these data matrices. So you've got the data sitting in here, and the argument of the functions, the psi x is just these basis functions of the dictionary evaluated at the x points. And then if you want to apply the Koopman operator over here, because the Koopman operator is just composition with f, and you know that y is f of x, you just trade an x for a y. So you trade blue for green, and that pops down here. And then if you roll through the algorithm, the EDMD, the extended dynamic mode decomposition matrix that you get at the end is the inverse of this matrix applied to this matrix. So what you're doing is this picture. So you start off with an infinite dimensional Koopman operator. You choose a subspace corresponding to the dictionary, which in this case corresponds to, the columns and rows. And you compress, and you get a finite matrix, and then you compute eigenvalues. Okay? So regardless of how well you compute the eigenvalues of this, or how much data you have, even if you have infinite precision in your computation, you can still run into this fundamental issue because of truncation to a finite dimensional space. So we can actually see this in practice. So here I've run EDMD for the Duffing oscillator, which is this two-dimensional ODE, system of ODEs. I've sampled at a discrete time step to get a discrete time dynamical system. And for my dictionary, I've chosen Gaussian radial basis functions. Okay, so just think of them as Gaussian bumps at different points. And I've used Monte Carlo integration, so that just means randomly sampling my snapshots. I've taken a lot of snapshots, 50,000 of them, just to get a very good approximation of these inner products or these correlations. And here I've shown the EDMD eigenvalues in blue for two cases. Alpha, which is this parameter here, this dissipation parameter. If that's 0, the system is Hamiltonian. The Koopman spectrum is the unit circle. Okay, so you get a lot of spurious stuff. If I switch on dissipation, I still get spurious eigenvalues. What you're seeing here in the contours, this is epsilon contour, where epsilon is that approximate point pseudo spectrum. So remember we had that set, where you could find these approximate eigenfunctions. So this is sort of giving you a certificate of how accurate these blue dots are. Okay, and I'm going to show you how you compute this certificate in a second. But you can track the error in the matrix size, and you see that EDMD doesn't converge. Okay, and this has nothing to do with finite data or the choice. Well, it does have something to do with the choice of dictionary, but it's nothing to do with sort of numerical precision or anything like that. It's purely because you're not controlling the error when you do that subspace truncation. Okay, so one of the things I'm very interested in is how do you do data-driven control of subspace errors for Koopman operators? Okay, and one way to do this is an algorithm called ResDMD, which I'll touch on briefly. So if we look at these matrices appearing in EDMD, we can sort of look at the color codes. We've got this correlation, blue-blue, blue-green. We can take the conjugate transpose of the adjoints, and we get green-blue. And then if we're staring at this, we're sort of thinking about, okay, is there something else I can do? Well, I can look at green-green, okay? What does green-green correspond to? It's when you're looking at the correlations with both of these guys forward in time. Okay, which if you go back to the quadrature interpretation, is giving you an approximation of this inner product, where you've got the Koopman operator on both sides. Okay, this looks crazy. Why would you want to look at this weird object? Well, if we go back to our residual, remember, we want these residuals to be small to get those coherent features we were seeing through the Lorentz attractor, right? So let's say I take a G that's expanded in my dictionary, like so. Here are the coefficients. And I look at the square of this residual. That's just this inner product here, okay? I can just take this expansion, plug it in, and I get this approximation here. So I can approximate this residual if I can approximate these types of inner products, right? And it turns out that under suitable conditions, as m, the number of data points, goes to infinity, if I just hop back a second, you've got different correlations here. You can represent this residual exactly in terms of finite matrices. L, which is this matrix here, the green-green matrix. A, which is the blue-green. And G, which is the Gram matrix or the blue-blue matrix. So you can control this subspace error, okay, or this infinite dimensional error, using a finite matrix, okay? Using the same data by just doing this simple trick. Okay, and that allows you to test the robustness of EDMD methods. So here we go. It turns out that you can, that there's a way of using that to build an algorithm that converges to the approximate point pseudospectrum. Okay, and then you can converge to the spectrum. Think of it as the set of eigenfunctions as epsilon goes to 0, and then you can show that it converges, right? So you can actually work out its error. So this is great. Okay, we have an algorithm that overcomes that subspace error. And at this point, I'm going to sort of pivot a little bit, and we're going to get a little bit more mathematical. So let's actually think about what we've just done. So I've considered a space of observables. So there's the allowed G of finite energy, this L2 basis, L2 space rather. And I can prove a theorem that says that there exists algorithms that depend on M, the amount of data, N, the size of the dictionary, okay, the subspace dimension that you're studying inside L2, so that in two limits, so M goes to infinity, then N goes to infinity, you get back this spectrum. For all systems, there's some mild conditions on the system that I won't get into, but you can think of this as a generic result. So this looks great, right? N, the size of the basis, N, the amount of data. But can anyone spot a potential issue with this theorem? Has anybody ever gone to infinity? Right? I haven't. Buzz Lightyear has. But it's really expensive, right? We've got two limits, M to infinity, N to infinity. Okay, so your first reaction is, okay, can I choose M depending on N or vice versa to somehow combine this and get convergence? And in some cases you can. But it turns out that in some cases you can't. Okay, so it turns out that for generic classes of systems, this double limit effect is actually necessary. Okay, and that's the next theorem that I want to get onto. So this is this area of adversarial dynamical systems. So you can build adversaries that disrupt Koopman analysis. So let's go through an example of this. So I'm going to study a particular class of systems. So these will be functions on the unit disk in R2, okay, that are continuous and measure preserving. So they preserve the standard Lebesgue measure on the disk. Okay, so think of that as volume preserving or area preserving. And they're also invertible. This is a very nice class of systems. I can even make F smooth. And this implies that the Koopman operator is unitary. Okay, so this is sort of the standard setting if you go back to sort of the algorithmic theory that happened before the sudden wave of interest in the data-driven stuff. So we have a class of systems, and I'm going to allow my algorithms to do a lot of stuff. So they can sample this function F anywhere inside the disk to any arbitrary accuracy that they want. So think of this as a perfect measurement device. Okay, so you can pick any point in your system. You can sample the system to any accuracy that you want. You can do that as many times as you want, whatever. So I'm being very generous to the algorithms, which means that when I prove an impossibility result, it's more powerful. Okay, because the algorithms have more power. So here's the theorem. So there does not exist any sequence of deterministic algorithms, gamma little n, using this measurement device, converge in a single limit to this spectral set that we want for all F in your class of systems. Now, I've changed notation here to little n, because here n can index anything. It's not tied to data. It's not tied to the size of the dictionary or anything like that. It's just a sequence of algorithms. Okay? So it could be, like the size of a neural network, or, the number of, the exponential of the number of times you sample or whatever, right? And this is a universal result, so any type of algorithm or computational model. There's actually a randomized version of this that says that even if you allow randomized algorithms that could, randomly sample the system or use randomization in the training, like stochastic gradient descent, you still can't get convergence with probability greater than 1/2. So what I'm going to do is I'm going to talk you through this version of the theorem, the deterministic case. And the way we're going to prove this theorem or at least give you the flavor of the idea, is we're going to build an adversarial dynamical system that stops our algorithms from converging. So this is very much in the same spirit as, adversaries in neural networks and things like that. Okay, so it's always a bit risky doing a proof in a talk, but if at any point you don't understand, feel free to break the rule and ask a question. So I'm going to start off with a system that's very simple to study, which is just rotation by pi, okay, in radians of the disk. And the Koopman spectrum of this is plus or minus 1. Now, in order to construct my adversary, I'm going to need what I call a phase transition lemma. Okay? So let me explain what this is doing. So suppose I have two sets of data points, x and y. They're distinct, and they lie inside an annulus strictly contained in this disk in R2. Okay? And they're disjoint. Then there exists a measure-preserving homeomorphism. If you don't know what homeomorphism means, don't worry, you can ignore it. H, such that H acts as the identity of this disk. So H is a map from the disk to itself, because it's transforming the disk. It leaves everything off the annulus unchanged. But on the annulus, it does the following to the data points x and y. So if you take the point x, you apply H, and then you rotate by pi, that's the same as applying H to Y. So if I imagine taking the inverse, H inverse over here, X is mapped to Y over H, F naught, H inverse. So if you've studied sort of conjugacy of dynamical systems and things like that, it doesn't matter if you haven't, you should think of this as like data conjugacy. So this is this homeomorphism, this sort of way of morphing the disk, is a way to make an algorithm think that the map from x to y is rotation by pi. Okay, and that's how we're going to trick the algorithm. Okay, so we have a very general theorem here. I've not said anything about what these algorithms are. So there's only one way you can start off a proof like this, right? So it's actually a little bit easier to prove these kinds of results. So you first suppose for a contradiction, a sequence of algorithms, data-driven algorithms, getting this Koopman spectrum exist. Okay? And I'm going to build an adversarial F that breaks this convergence. Okay? And this, by the way, the mechanism by which I'm going to do it is also partly inspired by the examples of EDMD not converging. So there is a two-way street between algorithms and adversaries. So let's start off with something that's a bit like rotation by pi, but I have a little bit of a bump here. So I'm representing this in polar coordinates. R theta gets mapped to R, theta plus pi, so that's the rotation, plus phi r. So that's this little bump function here. So it's compactly supported in this interval. And you can do a bit of analysis and you can show that the spectrum of the Koopman operator is the unit circle. So already you can see a real problem here. If we started off without this bump, the spectrum would be plus or minus 1. We add this bump, which can be arbitrarily small, and it's suddenly the whole unit circle. So the spectrum is a very brittle object, even for measure-preserving smooth systems on a disk, right? So one could argue, is it actually the correct object to try and compute? But that's sort of another story. Okay, so what do? We know that the algorithm, or we think the algorithm always converges. Okay, so we can apply the algorithm to this perturbed rotation. The unit circle definitely contains the complex number I. Okay, so that means that there exists some n1. We don't know how large, but it doesn't matter. So the distance of I to the output of the algorithm is bounded by 1. Okay, because we're converging to the spectrum. Now, gamma n1, when it's fed this algorithm, okay, it uses that perfect measurement device, but we know before it spits out the answer, it can only have sampled a finite number of times. It's allowed to adaptively choose that, do whatever it wants, but when it outputs the answer, there's a finite number of snapshots. So I'm going to let x and y correspond to those snapshots, and then I'm going to feed it into the phase transition lemma I had before. So take the lemma, h1 rotation by pi, h1 inverse. This is that homeomorphism, okay, that sort of change of the disk. Okay, now because of the way I've set it up, if we just go back, this equation here, f1 of x is the same as F1 tilde of X. They're consistent on the data. Okay? Consistent data, the algorithm is deterministic, it has to behave in the same way, so it has to output the same answer. Okay? So in particular, these outputs, so these sets, these sort of candidate eigenvalues, as you will, they're the same, so I can put them up here. So the distance of I to the output, when applied to this system F1, is bounded above by 1. Now here comes the problem. This H, okay, it's a homeomorphism, measure preserving. It induces a unitary change of basis, or you can think of a unitary similarity transformation for the Koopman operator. So the spectrum of the Koopman operator of F1 is the same as F0, which is plus or minus 1. Now, if we imagined putting plus or minus 1 here, the distance of I to plus or minus 1 is greater than 1. So there's a problem, there's a tension. So now what we're going to do is, remember, we wanted to prove there's no sequence of algorithms. So we have to do this on a cascade of shrinking annuli. Okay? And because my homeomorphisms are the identity of the annuli, I can do this in a consistent manner, and there's a well-defined limit. But the point is, for a sequence of increasing nk that go to infinity, okay, I'm always going to end up with this distance inequality. But this limit, the Koopman operator is unitary equivalent to the Koopman operator for the rotation, so the spectrum is plus or minus 1, so it cannot converge. So here's the picture. Okay, so you have a phase transition lemma, okay, and you're embedding this on a sort of cascade of annuli. And remember, this construction depends on your original sequence of algorithms, right? So it's an adversary for that particular set of algorithms you supposed existed. Okay, but you can use that to show that you can't get past this. Okay, so this is pretty pessimistic, right? And in fact, I'll maybe sort of go through this a little bit fast because it's perhaps not the right audience, but you can also start to classify dynamical systems and how hard these problems are, depending on the number of times you need to go to infinity, right? So we call this the SCI, the solvability complexity index. And you can get a precise class, right? So delta 1 will be one limit with error control, delta n plus 1, m limits, and then you kind of have ones where you can verify the output and stuff like that. But let's not look at that too hard. What I want to show is this. So if I take different classes of dynamical systems, okay, so for example, just continuous systems or continuous systems that are measure preserving or systems that have a modulus of continuity, sounds scary, but all that means is that the distance from fx to fy is controlled by alpha, a function of the distance of x and y. So it's telling you how much f can expand stuff. Okay, so if you've seen Lipschitz functions before, this would be an example. So if you know the system is measure preserving, that's this class here, you live here, and the gray scale here, SAO2, so you need two limits. If you know that there's a controlled regularity on the f, you also require two limits. But what's really cool is that there's a bit of maths behind this classification hierarchy that allows you to combine and mix and match definitions. So if you take the intersection of these two, so you assume measure preserving and a known modulus of continuity, then you sit here, and you can do it in one limit. And why can you do that? We go back to here. If you know how regular f is, you can control how accurate these approximations are for finite m. So you can adaptively choose m depending on n. So you can bypass this with additional assumptions. So the assumptions you have about your class of dynamical systems leads to different difficulties in how hard it is to approximate the Koopman spectrum. Okay. Where were we? Okay, so now I'm going to sort of pivot a little bit. So I quite like this quote. Sorry if you're French, but it's said with love. Mathematicians are like Frenchmen. Okay, so whatever you say to them, they translate into their own language, and forthwith it is something entirely different. So we're gonna be French, right? We're going to do exactly this. So far I've been looking at L2 spaces. So remember that thing I said about having a finite energy. I'm going to change the space of observables. I'm going to change the norm and the inner product that I'm working in with the goal of beating the two limits theorem. So if we go back to this impossibility result, I didn't really say it in the theorem, but it's important. I'm always working on an L2 for this result. So there's nothing saying that if I change the space, I can't get around it. Okay, so let's do that. We're going to work with something called reproducing kernel Hilbert spaces. Bit of a mouthful, but all it is a space of functions on your state space, so that for every x, every state x, the map that sends your observable g to g of x is a bounded linear map. Okay? So if you're struggling to think of an example and you've seen sort of PDEs or Sobolev spaces, that's an example. If you've not seen Sobolev spaces, quickly go to the Wikipedia page. There's a very nice page on that. But essentially, if you have a very regular function, you can put a suitable topology or inner product or norm, okay, on that space of functions so that this becomes bounded. But all we need is that there's a theorem that says that if this holds, then there's a kernel function. So a kernel is a map from x cross x to c, okay, where, okay, for each x, this is bounded so by something called the Riesz representation theorem. Evaluation at x is the inner product with some kx, some function, and then this kernel is built out of these functions like so. So you've probably seen kernel spaces in machine learning. Okay, so they're very popular because they can lead to ways to deal with high-dimensional systems. Okay, so this is typically the way people will use it, using the kernel trick. So you'll see here that I've got an inner product that's just coming from an evaluation. So it's very cheap if I can evaluate the kernel quickly to evaluate inner products. And that's really the thing I'm going to exploit, is the fact that there's no quadrature approximation of inner products here. So there's no M limit. Okay, word of warning. If you change the kernel, you change the space of observables in infinite dimensions. That really matters. Okay, so the norm or the Hilbert space that you're working on changes the operator and then changes its spectrum. Okay, so there's a lot of work at the moment in the Koopman community studying the theoretical properties of these Koopman operators and the different kernel spaces. I'm not really going to get into that, but you can often you can choose the kernel to emphasize the dynamics that you're interested in. Okay, so there's a lot of interesting work. So let's go back to our green slide. And I'm going to use sort of a very nice duality formula. Okay, so if I take the adjoint or the complex transpose of this Koopman operator and apply it to this kx, so remember that's the function here that's generating this linear functional. This is just k of f of x. So the adjoint of the Koopman operator, which is sometimes called the Perrin-Frobenius or transport operator, is transporting x to f of x in kernel space. Why is this useful? Well, remember I have snapshots. X, blue, y, green, y, f of x. So, for example, suppose I want to take the inner product between kxk, kxj. This is just the kernel function of xk, xj. Now, if I apply k star on the left here, I use this formula to get ky, and then I just trade green for blue. Sorry, blue for green. And then if I want to get this matrix I had before with k on both sides, the green, I apply k on both sides, or its adjoints, and I get this like this. So I can represent this residual exactly using these matrices without any large data limit. Another way of thinking about this is that I've coupled m, the number of snapshots, with n, the size of the dictionary. Okay? And I don't have to worry about how many data points do I have to get before I can really trust an observable and things like that. So you can wrap this into an algorithm. Okay, so you take this residual squared. Okay, and over a grid, a computational grid of candidate eigenvalues, you can minimize this residual. Okay, so you minimize over the G here, the observable, inside your space. Okay, so a linear combination of your kernel functions. This boils down to something called a generalized SVD or a generalized eigenvalue problem. So there's lots of numerical toolboxes that can help you. So you can do this very easily in Python. And then you output the points of your grid where this residual is smaller than epsilon. And here's the theorem. So you can show that your output's always contained in the true spectral set, so you never make an error. And you also converge as n or m equivalently, so n equals m, goes to infinity. Okay, so you can bypass that two-limit thing by changing the space. Okay, so super simple idea, and you get this theorem. Okay. So I'm going to show you what this does in practice in a second for an Arctic sea ice example. But let me show you a really complicated slide, first of all. And I'm not sort of going to try and explain everything on this slide, but what I'm trying to get across is that the spaces make all the difference. So here we have this crazy hierarchy, right? We can do it in one limit with error control. One limit, we need two limits, we need three limits. Don't worry about what all these symbols mean. They're just different subclasses with different complexities. Think of these as complexity classes. So we take L2, our original space. So this is sort of the classic Koopman space that Koopman and von Neumann were working on in the 30s. And then we can sort of place, remember that diagram I had with the different dynamical systems? Okay, so if F is just continuous, it needs three limits over here, right? You have to go to infinity three times, no hope. Here it's a little bit better. Okay, so you only have to go to infinity twice. Still very expensive. So measure preserving, modulus continuity. Remember this combination. Now, what happens if I change to RKHS, that's this kernel space, everything sort of shifts to the left. Okay? So you're reducing the number of limits. And this is all for epsilon equals 0. So think of these as getting exact eigenfunctions. If I only want pseudo eigenfunctions, told you it was going to be messy, I get this. So the blue dashed is pseudo eigenfunctions. And again, you see it's going to the left compared to the red. Okay? So depending on A, your space, B, the assumptions you make, and C, what you actually want to compute, it can be easier or harder. Okay? So we can now start to classify how hard these problems are. So each of these classifications comes with a convergent algorithm giving you an upper bound on difficulty and an adversarial dynamical system giving you a lower bound on the difficulty. Okay, so no more math. Let's actually look at an example. So I'm going to look at Arctic sea ice forecasting. So I'm going to collect a bunch of satellite data over the last 40 years. And I'm perhaps interested in this if I want to, save the polar bears or work out, trade routes or something like that. The problem with this is that it's very hard to figure out when you're looking at this dynamical system which geographic regions are significant. It's a very complex, nonlinear, noisy system. And it's also very hard to predict sea ice more than 2 months in advance. So my data is going to consist of a grid, I think it's 25 by 25 kilometers, over the Arctic region. And on each grid point, I have the sea ice concentration averaged over a month. Okay, so I have monthly data for the last 40 odd years. Okay, so if I apply this kernel method, and in fact, what I'm going to do is I'm going to apply delay embedding before doing this kernelization. It's often a very good trick. In fact, 6 delays is good because it captures the half-yearly cycle. I get this picture. So these are the EDMD eigenvalues. They're plotted on a logarithmic scale to take into account the time stepping, right? So to map consistently as I vary the time step that I collect data. I've colored them all in green to red, corresponding to the eigenvalue error, so that residual that I can compute, right, using that green trick. And you have a lot of garbage. I've highlighted in blue ones with small residuals. So this up here is the sort of dominant monthly cycle. So it's got a period 12, which is why you're seeing 12 eigenvalues. Okay, so that of course corresponds to the year. And you can look at the Koopman modes corresponding to these. So these give you sort of the geographic regions of interest. So it answers that question of how do these different regions interact. So here you've sort of got the first month, second month, and so on. But now each of these associated an error, right? So I know how much I can trust this picture. And in fact, you can even look at stochastic versions of Koopman operator, and there's a nice variance interpretation of this residual as well. But I'm not going to go into that. And I've got the mean mode. Okay, it's sort of a bit boring. It's the average. But here's what's really cool. So amongst this sea of rubbish, there are these sort of hidden modes that you can detect using this residual. And if you then plot these, we were very surprised. So there's a lot of studying, I think it's called the Barents Sea. I'm not a ocean person, but apparently this sort of region, how it interacts over here is a well-studied thing in the Arctic. And there's lots of interesting papers trying to figure out that mechanism. And we're able to extract it very easily using this DMD stuff. And this is agreeing with other studies that have been done as well, non-Koopman methods. Okay, so it works on a real world noisy example, but we can take it one step further. Remember, I had that slide right at the start where I was trying to get these pseudo eigenfunctions and forecast, right? So if I could expand the state or the observable in these pseudo eigenfunctions, I could march forward in time by taking powers of the eigenvalue plus some error. And if we go all the way back, the key point I want to make, and I perhaps should have put again so I didn't have to go back, is, yeah, the error here. So it grows linearly in n, okay, the time that you forecast, but the smaller epsilon is, the smaller the error, right? So epsilon is sort of inversely proportional to how long you expect to be able to forecast at a reasonable level. Okay, so I'm going to try and clean up this EDMD using the residual. And I'm going to try and forecast the whole sea ice concentration. Okay? And I do that and I get this picture here. So let me explain what's going on. So we're forecasting the sea ice, and then for each grid point, okay, we're testing whether the grid is covered in ice or not. There's a 15% threshold, which is sort of the standard benchmark. And this will give us a binary problem, right? Is that grid covered in ice or not? And then we look at the accuracy. So higher accuracy is good, averaged over the lead time, so the forecast time for unseen data. Okay, so I feed it. I've not given the precise dates, but you can find the paper. And I'm forecasting in time. And this is what we get. So in red is sort of a pre-neural network AI dynamical systems model, CS5. In blue is something called IceNet, which at the time we were writing this paper was sort of like a state-of-the-art neural network-based method. Very expensive. You have to train for days on lots of GPUs. The Koopman, the method that we're using, this cleanup method, we can train instantly on my old rubbish laptop. Okay, we're only using a 500 by 500 matrix, and we're getting a really good flat line here. Of course, it's going to deteriorate eventually because it's a chaotic, noisy system. But we can use this residual to filter out the wrong eigenvalues. And we can, in fact, something we played around with was using the residual to sort of train the kernel and things like that. So you know whether your dictionary is doing a good job. Okay, right. So very quickly, the last sort of 5 or so minutes, I wanted to chat a little bit about where this work is going for forecasting and dictionary learning. And this is something that we've been doing with Steve as well. So you can replace the singular value decomposition that you often use in DMD type methods with something that we call the principal angle decomposition, which is a way of measuring the invariance of your dictionary when you apply the Koopman operator. Okay, because the problem is you compress the Koopman operator to a finite matrix, you march forward in time, your observable might go outside that initial subspace, right? So you've always got this error when you march outside the subspace. And this is a way of tracking this down. Okay, so the principal angles are related to the sort of the analog of singular values in this decomposition, and the vectors are giving you sort of the observables or the linear combinations that are best kept when you apply the Koopman operator. Okay, and you can do this, and you can get better accuracy than for an SVD compression based on the number of modes, right? If this is duffing the Lorentz, big wall of text, but the point here is that you're using the same matrix, this green matrix, to track the subspace error when you march outside your initial dictionary. Okay? And we can use this to get error bounds on forecasting. So we looked at an example. Here's Pluto. I think it's no longer a planet. It was a planet when I was at school. It might be a planet in the future. But the key point is there are 5 satellites. Okay, so 5 moons or whatever going around Pluto. It's the two. I think. Sorry, the most dominant one, Charon, is of a comparable mass to Pluto. So you get this sort of complex 2-body system. Okay, so it's a chaotic system. And what we're going to do is we're going to use ideas like this to get an L2 and kernel space forecast for the dynamical system. Kernel spaces are very useful. So remember, point-wise evaluation was bounded in these kernel spaces. So forecast errors give you point-wise errors for trajectories, not just L2 errors. Okay, so here's an example for, I think we're tracking like the first coordinate of this moon or something. If you're interested in this plot, email Gustav. And here's the actual error in the Koopman forecast. Here's our error bound. Okay, so first thing to note, the bound is above the true error, which is great. Okay, so the maths is working. Second thing, it's kind of a big gap, right? Especially on a logarithmic scale. It's a bit disappointing. So what we can actually do as well as this is start to look at Gaussian processes to try and figure out what's the average error you make when you march outside your subspace. Okay, so how does that subspace error averagely behave? And you can do that, and you can send it through the same analysis, and you get, ooh, this error here, but also with some variance bars. Okay, so you can get good proxies for how good your Koopman forecasting is. Okay, and then we can turn this into a whole sort of pipeline. Okay, where we take the error bounds and then we train the kernel. So we were looking at a kernel function. Okay, to try and reduce this error as much as possible, and that can lead to better forecasts. Okay, so we're now at the stage where you can control this forecast, this spectral error, all with this green matrix, and get a whole thing that allows you to sort of select a good dictionary. So I think that's where I want to sort of stop on the actual science. I'm going to end with 2 very shameless plugs, and I apologize, it's very un-British of me. But there's a book coming out in August on computing spectra, which includes a meaty chapter on Koopman operators. Okay, so this will give you sort of like a comprehensive overview of not only the maths, but also the practice. So I'm a firm believer that, you want theory and practice to interact with each other. Okay, and that's really helpful. So if you're interested in this book, chat to me. There'll be algorithms, full code, loads of examples and exercises as well. So I've been using it as a textbook. Okay, the second shameless plug is that in August, if you're wanting something to do and you want to escape Seattle, come to Cambridge, okay, for the summer. It's a beautiful place. You can punt. But you can come to the Isaac Newton Institute and learn about operators and spectral theory and all machine learning, all these things in dynamical systems. We have a month-long program, probably just about see the organizers. If you're interested, again, either email me or apply to the Isaac Newton Institute. We have some spaces still available as well. And this would be a great way to sort of, I think, collect a lot of people working in different areas. So we have some very sort of hardcore spectral theorists, and also some, very, very sort of applicational people as well, and people in the middle, and we're hoping to get a bit of a nice mix and sharing of ideas. Okay, so to summarize, data-driven spectral problems for Koopman operators are hugely popular. So there's thousands of papers on this. But if you're not careful, standard truncation methods can fail, and this is due to the subspace error. So you're dealing with an infinite dimensional object, okay, and you're doing a finite dimensional approximation. So you need to go infinite dimensional. So think Buzz Lightyear. General methods with convergence for spectral properties, this green matrix. You can do things for continuous spectra as well, and spectral measures. I didn't really talk about that. But if you're interested, chat to me afterwards. And then you can wrap everything into this hierarchy that classifies how difficult these problems are. So you get lower bounds and difficulty through adversarial systems, So I walked you through the mechanism of one of those proofs. You get upper bounds through infinite dimensional algorithms, or rather algorithms that respect the infinite dimensional object you're dealing with. And it's fair to say that we now have a pretty complete picture of at least computing spectral properties. There's lots of other interesting problems like control and stuff like that on L2 spaces and RKHS spaces. Okay, so lots of people in this community have been working on these two spaces. And the matrix L, that green matrix, also allows you to control forecast bounds and train dictionaries that led to this principal angle decomposition as well. So I think that's a good time to stop. Thank you for bearing with the sort of mix of maths and applications, and I hope that it was at least enjoyable. Thanks.
Basic question, but how do you go from forecasting observables to forecasting the state?
Oh, yeah. So, yeah, that's a very good question. And it's not as trivial as you might think initially. So let's go back to here. So my observable G lives inside some space of functions. Let's suppose your state space is a subset of RD. If it so happens that those D coordinates as functions also lie in the space, then you could vectorize this, right? You could just do this for each one. You have to be careful if they're not inside the space, and that's where the subtlety arises. So you're always, when you're doing forecasting, you're implicitly assuming that your sort of coordinates functions live inside the space of observables, at least in infinite dimensions that you're working with, and can be approximated by these pseudo eigenfunctions that you get.
So the idea would be in your working basis, you would include like.
Good, yeah. Exactly. Or you could like project the coordinate onto the space and then do it, or but typically that way of actually including that in the subspace works best. So what you do is you take the coordinates and then you might take a delay of the coordinates, augment to a bigger space, and then do something afterwards like a kernel method or something like that. But as long as you keep those coordinates, they're living inside your subspace, your dictionary, and then you don't have to do the projection.
Subset in a sense, or else, because the point about like the function like X is not.
Exactly. Yeah. So there are some subtleties there. Yeah. And in fact, even getting a bounded Koopman operator on reproducing kernel-Hilbert spaces is very tricky. So there's a lot of nice work by Karl Worthman and his group in Germany, where, what am I trying to say? So if I go to, I didn't really dwell on it. Where was it? Here, yeah, we're using something called a Matern kernel. It's like a hypergeometric function or something, I can't remember. But the point is that this is one of those examples where they've proven nice properties about the Koopman operator being bounded and things like that. And you have to worry about compactness and all this stuff. But it's a reasonable assumption that for the Arctic, you're not going to have. Well, in fact, it is compact because your concentration cannot go below 0 or above 100. No, I use a poly-Gaussian kernel, and I actually didn't prove that it's. This was a more applied than mathematical paper, so I just. Yeah.
Is it only for the Matern kernel?
No. So when I said here that the community is heading in this direction, there's a lot of open problems about which kernels lead to nice properties of Koopman operators. Yeah. It's poly-Gaussian, probably theoretically, unless you're on a compact domain, isn't going to give you a nice thing, but at least for this type of dynamical system, it works quite well. Yeah. And you can always check, if the residual is small, you've done a good job. So, yeah. Oh, this one. Right. Yes. So. You start off with a space of functions. So these are your observables. and you only assume one property, that if you pick any state inside your state space, the map that sends your observable G to G of X, so that's evaluating at that single point. If you assume that's a bounded map, and by bounded I mean as you vary the observable, then there's a theory that tells you the inner product is induced by a function. So you've swapped out inner products or integrals, which can be expensive to evaluate with data, to evaluating just a function. And that's really what's behind this kernel trick, which is very popular in machine learning. Another way of thinking about it, which I haven't written here, is there's actually there's a feature space interpretation of this, where you're mapping to a different space. You're doing linear stuff over here, then you're mapping back. So if you go to again, Wikipedia is really great at sort of mixing the maths and applications, and you look at kernel methods, it'll explain that. So a concrete example, have you seen Sobler spaces? Okay, so have you seen CK spaces, so functions which have K derivatives? Okay, so if you start off with a big space of functions and you progressively assume more and more smoothness, there eventually becomes a point where it's so smooth that this boundedness property is satisfied. So you assume more and more smoothness. Eventually, bang, there's a kernel, okay? And that means that you can apply this trick. Okay, so why is this useful? So we've got an inner product, or this correlation, evaluated exactly in terms of this kernel. Remember that when we're sort of building these matrix approximations, we need the correlations between, so think of these guys as just different functions or elements in my basis. You need correlations between these for different k and j, and you need, the Koopman operator here on the left and on the right down here as well. But you go through the math, you get these three correlations. Now before, for the old L2, so think of that as like observables with a constant energy. So you're not assuming smoothness. So that's actually another way of thinking about it. Kernelized methods, you're assuming smoothness on the observables. L2, you're assuming they have a finite energy. So their square leads to a finite integral. So there's two different mathematical assumptions, two different flavors. Okay, so you assume that, and then you get these inner products. Now remember, we increase when you're sampling, you also have to sample the inputs. So it can be very, very expensive. And in fact, there is a way to recast the control problem as just an autonomous dynamical system, but the state space becomes infinite dimensional. So not just the observables, but the state. So it's messy. So at the moment, this is something that also working with Steve and Gustav and Nicola on this is trying to figure out, how can this help for control? It's certainly the case, I imagine, that if you have a smaller subspace error, then your linear approximation is doing a better job. So it stands to reason that maybe perhaps you'd expect control to behave better if you've got a better finite dimensional approximation. And really, the whole point of doing this Koopman is that you get a linear control problem. That's a lot easier to solve computationally. But beyond that, yeah, that's again. So I had to be a little bit careful with the end slide. So we're now at the stage in the theory of this operator where we have, in a numerical theory, where we have a pretty good handle on computing spectral properties in these different spaces. But control is really outside of that, so that's sort of the next step. Oh, sorry. Cool. The first person who uses that joke.
There you go.
Mm. Mm-hmm. Yeah. So it also depends on what you want to do, right? Do you want point-wise forecast bounds, in which case you can't really do that in an L2 case? Yeah. The sort of the honest answer is it depends on the system. So a lot of this is choosing the dictionary, choosing your observables is a bit of an art. So what this green matrix, this residual, can tell you is it gives you a certificate. As you saw that at the end where we were training a dictionary, we can also do the same thing in L2. You might not know before you do that training which is going to be better, but you can hope that if you get the error afterwards, that you can then, pick the better one. So it depends. So, for example, if we look at Lorenz, this coherent picture we had, it really doesn't make sense to do an RKHS on this space, right? This is a very nice measure-preserving system. It's got something called a physical measure on this attractor. So that's an invariant measure that also means that if you start off a trajectory near it, near the attractor, then you'll have the ergodic theorem as you collect more and more samples. Okay, so there's very nice statistical properties all wrapped up in the L2 space. I didn't really talk about this, but there's always measures, right? We always have a measure here. So the omega Lorenz is statistical. So typically L2 is great for low dimensions, but when you go to high dimensions, like that Arctic sea ice, I wouldn't really know how to do L2 on that properly, to be honest. Not just because of the kernel trick, but you're gonna, if you want to collect data to get quadrature, how do you build quadrature in high dimensions? You're going to run into the curse dimensionality. Yeah. The eigenvalues. Yeah. Yeah, absolutely. Yeah. Yes, because the amplitude can be misleading because of this subspace error. So actually, that's another way of thinking about this plot here. The SVD is truncating according to amplitude. Here, right? This PAD is truncating according to subspace error. So it's kind of counterintuitive that if you're looking at the amplitude, that doesn't always give you best compression because you leave finite subspace. There's always an implicit projection.
Okay. There's no more questions. There's 1.9. Finally, thanks for the talk. In slide 47, those that learn dictionary span Koopman environment space with 1.6.
Well, so no. Right, because the error is increasing. Wait, no, sorry, I should rephrase that. Here I'm, of course, taking the observable I was interested in projecting onto the subspace and then doing. So okay, so this plot doesn't tell you no. But I'm pretty sure, I mean, so finding exactly invariant subspaces is very rare. Almost never happens unless you have a very sort of clean analytic example. So I would probably, bet a huge amount of money that the answer is no without even bothering to check with Gustav. But you can certainly check the residuals, right, and things like that. And in fact, there's PAD expansion here, right? And that will tell you if all of the angles are 0, you've got an invariant subspace. But you can get an approximate invariant subspace. So that's sort of what this is giving you, is the next best thing, right? Something that's almost invariant.